Okay, so now we're starting in probability. And I hate to say this, but this is a section that people dislike the most. How sad is that?
This is like the only section I actually enjoy, I think.
Well, there you go. So I'm on page 142. And again, you know, the definitions will show up. They're marked in blue. So when we talk about probability, what would be the probability of snow?
No,
What would be the probability of it snowing here? 0. You cannot get any smaller than 0. So you can't say the probability is -5. We're just saying that the chances of snowing is 0. And the chance of seeing sand in Doha, 100%. That's the range, 0 to 1. Nothing beyond that. And I want to repeat that as many times as possible because sometimes your calculator gives you a p-value that would be 5.6. And if you read to the very end, it has e to the -6. What would that be? So it looks like this. If am I writing? Gosh. Yeah, so maybe I can just do it. So it would be like this, 3.56, and and it does this, doesn't do, it does e -6. What that means is that it's 3.56 times 10 to the -6, so it's basically this, right? In other words, 0. Don't you ever write me a 3.56 answer for a probability. It just cannot be 100%, you know. I know people will brag and say, oh, I've put 110% effort into this, but we know they can't do that. All right, so the probabilities begin at 0 and they end at 1. You know, if I flip a coin, what's the chances of me getting ahead? 1 and 2, right? I've only got 2 choices. No matter what you see on TV, what you see in the stock market, every time I flip that coin, my chances are 1 and 2. Even if I've flipped 5 heads in a row. When I come to flip again, there's nothing that says, well, okay, she's flipped 5 heads, this next one's got to be a tail. Every event is unique unto itself. Okay, so we have also the word experiment. Process that leads to the occurrence of one and only one of several possible observations. So let's talk about the coin. That's an experiment. I want to see how many heads I would get if I toss the coin 50 times. The reason we identify it is so that I can draw a distribution table. I'm only talking about heads. I don't care about the tails. Or if I was talking about the number of people that chose the red ball, that's all I care about. If they chose other colors, I don't care. So in an experiment, we define what we're looking for. And an outcome, in my example, the outcome is either a head or a tail. So I'm only counting the heads. An event is a collection of one or more outcomes of an experiment. So let me see if I can make a nicer picture here on whoops, gosh. Let's try a new note page. Let's use some ink. Come on. Why can't I do this? What's wrong with it? Doesn't like being over here. Okay, so I could do something like this. And I'm going to put in the number of heads that I could possibly have. And here I'll just count, I'm just going to count them, right? So this is like a frequency table we've done before. And I would just put it in like this, with straight lines maybe. I'd flip the coin, it would be yes or no, and I would count the probability. Is that okay? We'll do a load of them, so there's no worry. Now we're coming into some words you've heard before. I'm on page 144. And classical probability is based on the assumption that the outcome of an experiment are equally likely. And when I toss a coin, it's equally likely that I get a head or tail. If I roll a dice, it's equally likely, unless it's loaded, that I can get 1, 2, 3, 4, 5, 6. So in this case, we just take the number of heads and divide by the number of tosses, and that would be the chances of getting a head. I might even have a coin. Does somebody have a coin? And let's just count the number. This isn't working well. I think it doesn't like being so far away. Okay. So does somebody? Nobody? You have a coin?
Yeah, I think.
So let me get a new page here, so I can start nicely. Okay, do you want to start tossing somebody? Okay, wait, I gotta count.
What do I call head and what do I call tail?
Okay, so I will put both in, and then at the end we can get the number of hits, okay?
Push harder when you're writing.
Okay,
All
flip
right.
then,
Tails. How many times am I doing this?
as many as you can.
Heads. Heads. Tails. Tails. Heads. 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 Tails. 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 Heads.
Let's do 20.
Heads. Heads. Tails. Tails. Heads. Tails.
2 more, 1 more.
Heads.
Okay, so if we were going to talk about this as being classical probability, in this case we'd say the probability of getting a head in this case would be R11 over 20. Yes? No secret here, nothing magical, and mutually exclusive. Our favorite word again. It means that something can only be in one class. So if I said what would be the probability of getting a queen on a pack of cards, so let me write that one. So this would be, what's the probability of getting a queen? How many queens are there in a deck of cards? You don't know what a deck? 4. So this would be 4 out of 52. Straight classic, it would be my chances of getting a queen. If I then said, what's the probability of getting a heart? That's one of the suits. More than that. Well, 1 in 4 or 13 out of 52. And here, I'm quite happy if you leave these fractions just like they are. You don't need to reduce them or put them into a decimal. I'm happy that you know that there are 52 cards, and out of those 52, there are 13 hearts. That is fine with me. If I now said to you, what's the chances of getting a queen or a heart, or means it could be either one of those, these are not mutually exclusive. Do you see that? Because I have the queen of hearts. So I would have to fix this. I would have to fix it, right? The rule would be that well, I'll do it later, but I just want to tell you, because these are not mutually exclusive, I have to look at the fact that the queen is counted in the first group and the queen is counted in the second group. So we have to take her off at least once. Yeah? So here, mutually exclusive is going to really change the formula we use. If they are mutually exclusive, so let's say the probability of getting, a Christian or a Muslim. Those are mutually exclusive. So if we were to count in this classroom, how many Muslims do we have? We have 8 out of 11. So that would be 8 out of 11. And Christians, 3. So we would have so the possibility of getting one or the other, because we don't have any Hindu or Tao or anything else, is 1. Do you see? It's mutually exclusive. I don't have to worry now that one of us appears in both groups. So I'm suggesting you write an example that makes sense to you. Back to the Queen of Hearts, I could have also said, what's the probability of getting a female or somebody in business? So here, again, those are not mutually exclusive, because I have a man that's in business? Are either of you in business? No. But I have women that are in business, yes? So they would be counted twice. They'd be counted as women and they would be counted as business. So in that case, I need a special formula. So we'll be at that special formula very quickly. I just want you to know that mutually exclusive now means something to us. And collectively exhaustive, we know what that means as well. If I were to, let me get rid of a new page. Quite haven't got this down pat yet. Okay, so let's assume that I tossed a coin 3 times, and I want to write all the possible number of heads that I could get. All the possible number of heads I could get in 3 tosses. Okay, so what could I get? How many? I could get 2. I could get 2. I could get all heads. What else? I could get 1. 0. Collectively exhaustive. If I don't write all of the options given when I toss the coin 3 times, i.e. if you leave 0 out, this will not be collectively exhaustive. And when I do the probabilities, I will not add up to 1. That's how I know I'm correct now, because if everything is given, then it tells me that this must be a total of 1. So I would be writing the probabilities here of getting ahead. And this total must equal 1. Okay, and we have empirical probability, which is on page 145. And that would be the one that if I said to you, I know the chances of getting ahead on 2 coins is 1 in 2, because the empirical data has shown us that. And the law of large numbers just means that we've done it a gazillion times. We'll come back to those anyway. And the last one, subjective, would be, I think it's going to rain. That would be subjective. I have absolutely no empirical data. I have no magic wand. I'm just telling you I think it's going to rain. Same way as if you work the stock market, the people will tell you that they believe a stock's going up. They may have something hidden. I'm dubious of that. So I'm ready to start on page 149. And we'll come back to the words again anyway. So we're going to start with, we call it the special rule of addition. Oh, maybe I need some ink. Okay, so we'll do the one for addition. And first of all, let's make sure that we know what these symbols mean. If this were like this one, or, it means either or. And if I have and, it means they must have both. The first one is or. On page 149, it's or. Has the word or written between it. Okay, so I'm going to draw some Venn diagrams because they make it a lot easier for us to see. So, and in this Venn diagram, I'm going to have one circle, which I'm going to call A, and that's going to be the number of women in this class. 1, 2, 3, 4, 5, 6, 7, and including me would be 8. So I could put 8 little marks in here. and I'll make that women. And now, if I were to make one for men, these two circles will be not intersecting in any way. Two distinct circles. And so here for men, here I would have 1, 2, 3. And this we call the universe, is the sandbox that these pictures are in. And it means that if there were some other creature in this class, alien of some kind, they would be outside of our circles. Do you see? Because the circles may not include everybody, because I might want to do something that has something to do with business and IT, and I might have health science students here that will then end up being in the sandbox but not in a circle. So in this particular special case, if I said the probability of choosing a woman or a man in this particular story, we consider it a special because all I have to do is add the probability of getting a woman to the probability of getting a man. So it looks like this. This is called the special case because they are mutually exclusive. And my Venn diagram shows them mutually exclusive, yes? They're out here, not together. And so in this case, the chances of getting a woman is 8 in 11, and the chances of getting a man are 3 in 11, and therefore our chances of getting one or other is going to be 1 in this case. Let me draw another one that could be mutually exclusive where we would have 3 choices. So let's say that in here I'm going to look for just let's see. I'll do this one for business. So who's in business? 1, 2, 2. And how many in health sciences? All the rest? Okay. So since Adam and I are in neither, I'll just make this 9. Okay, mutually exclusive. Anyone not see that? They're not intersecting in any way. Okay, so if I were to say, what's the chances of me getting either business or health sciences, I would add the probability of business plus the probability of health science. Special rule. Any questions? So here it's going to be 1 again because we don't have anyone else here. So, sorry, that's 2 in 9 plus 7 in 9. What if I were to draw one that looked like I was going to do women, so I'll put them in this one. One, 2, 3, 4, 5, 6, 7. And I'm going to add business to it. If I did that, I would end up having this picture. And there's only 2 women, there's only 2 in business, and they're both women, right? So in this case, if I said, what's the probability of a woman or business, this is not a special case anymore, because if I do it like I did previously, I would count these 2 women twice. You see, it would be the probability of women, which we already know is 7 in 9. And if I add the 2 in business, that's 2 in 9. Whoops. But I've counted them twice. So I need to now subtract those 2. So I'm ending up with 7 in 9. And let's see if that's correct. So you either have to be female or you have to be in business, either or to be counted. So 1, 2, 3, 4, 5, 6, 7, and no one else. Do you understand the difference? In this story, these 2 would have been counted twice. So we don't get to use what they call the special rule of addition. I must subtract them. If you look at it from a Venn diagram point of view, you're just going to count the number of x's that there are. Because in the Venn diagram we overlap, I will not be counting those two twice. So I'm just going to count the number of x's in the picture, and it's 7 out of 9. Let's try another one. So let's say that in, oh, ink. I'm getting better. Okay, so what if we did the number of categories in one circle? So this would be them. How many? 1. Okay, so 1. And then if I chose health sciences, are you not a category? 2, 3, 4. Was that a bad question? Okay, 1, 2, 3, 4, and then if to that I add health sciences. If I were doing some project to see what would be the probability of finding a category in health sciences, then health sciences is going to come like this. Correct? These 2 women over here that are category are in business. And so for health sciences, I need 5 more here. Okay, so if I were now going to say, what's the probability of finding a category or health sciences? Again, not the special rule, because otherwise, if I counted this up, I'd have more, the probability would be bigger than 1. So instead, just count the x's, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 9. So in here, we are either category or health sciences. This is a unique class. I can't get anyone out of it. If I asked this, what's the probability of finding a category in health sciences? I would use this and. So that means you must be both. You must carry both characteristics. And what would be that probability? Out of? 2 out of 9. And it would be the 2 men. Do you see? It's a lot easier to see this if you actually see the people that are being represented by what we've drawn here. Okay, let me. Okay, your book has some other well, I can wait. I can draw some others. Oh. Just some other words that we have, because sometimes it's easier to use a complement with an E, not a complement with an I. So if this box contained the students in this class, so 1670-1, or are you -2? 2, I think. If it contained all the students of 1670-2, and in here, I want to count all the categories, I would have 4 marks in here. So if I want to know the probability of not finding a category, this is a symbol. That means not. It's the complement. It means what makes up the rest. In this case, it would be 5 out of 9. And a lot of times it's easier for us to say, for the flipping of the coin, what's the probability of not getting ahead? Could be that we subtract all the others from 1, all added up. Or we could say, what's the probability of at least getting 1 ahead? Then I can take 0 away from it all. So that's the complement. So you have all pictures drawn here. So on page 151, so maybe I'll draw another one. It says to you, what's the I'm looking at the self-review. A sample of employees of worldwide enterprises to be surveyed about a new healthcare plan. The employees are classified as follows. Is it possible that a supervisor is also a secretary? No. Mutually exclusive. Their roles in this worldwide enterprises is unique unto itself. They are not playing two. If I were to draw a Venn diagram, I would end up having 5 unique circles inside the box. Yes? Mutually exclusive. So here it says, what is the probability that the first person is selected is either in maintenance or a secretary? So the number of people in maintenance is 50. The number of people as secretarial is 68. So the chances of getting one or the other, so the probability of being in maintenance or secretarial, because they're mutually exclusive, is the same thing as me doing this. So I would get 50 out of 2,000 plus 68 out of 2,000. So altogether, 118 out of 2,000. And again, I don't care if you leave it like this. It's a lot easier to look at when you're done if I don't cancel this down. I know how I got the 118. And if it says not in management, this is where you would use a complement. So I know that all of them must total 1. So from it, I'm just going to take away the probability of somebody in management. So that's 1 minus 302 over 2,000. So it's 2,000 over 2,000 minus 302 over 2,000. So 1698 over 2,000. Do you see where that's a lot easier to use the complement rather than me add up the supervisor, maintenance, production, and secretarial? What do you want me to do?
Don't write so much.
Don't write so much?
No, don't write so much at the bottom. It's hard to see when you write at the bottom. Your eye
Oh, of course. I won't write so much next time. Okay? So let's look at the picture of Disney and Busch Gardens, where they're saying that there are some people that go to Disney, there are some people that go to Busch Gardens, and then there are some people that go to both. That's the same story of our Venn diagram as we had before. So we would add a new page. So here, the probability of going to Disney, and I'm going to write these so that we use our symbols correctly. The probability of going to Disney is 60%. The probability of going to Busch Gardens is 50%. At this stage, can you already tell that there must be some people that are really having a good time and have gone to both of them? You know that because the total is 1.1. So by this we know that they're not mutually exclusive and that if you go to Disney, you can still go to Busch Gardens. So it's telling you here that the probability of going to both, that means that Disney and Busch Gardens is 30%. So if I were to draw a Venn diagram to represent this, whether I do it in percentages or people, it doesn't matter. If you're unhappy about the percentages, let's talk about 100 people then, and so we won't have to deal with that. So here's Disney. They've got 60 people, and a Busch Gardens got 50. But when we draw these Venn diagrams, we start in the center. How many people went to both out of my 100? 30. So I have 30 people in here. I just said I had 100 people, so I multiplied the 30 by 0.3. If you, decimals are fine here. If you just wanted to put percentages in, that's okay as well. So if 30 people went to Disney and Busch, how many people just went to Disney? Well, my whole circle for Disney must be 60, and I've already used 30 of them up. 30, yes. And in Busch Gardens, I must have 50 altogether, and yes. Now, once you put this in, can you already see now, if I were to say, what's the probability of finding that someone that went to Disney or Busch Gardens, I'm going to add what this is up without repeating it, yes? So 30, 60, 80. So it would be 0.8, or 80 people out of 100. That's from the Venn diagram. Do you see what's happened? Because I'm overlaying the circles, I'm not counting those 30% of the people that went to both activities. If I were to write it as the formula, it would be Disney or Busch Gardens is equal to the possibility of Disney plus the possibility of Busch Gardens minus the possibility of Disney and Busch Gardens. This is considered to be the addition rule when it's not special. I'm almost forgotten what I said I was going to do, not write low. So it's 0.6 plus 0.5 minus 0.3 is equal to 0.8. So whether I draw a Venn diagram, so with the Venn diagram, you see, once I put these pieces in, this 30 is overlapped. So I can just add 30, 60, 80. If I do it in the formula, then I'm saying I want the probability of Disney plus the probability of Busch Gardens, and then I'm taking away all those people that attended both. So that's why for us, mutually exclusive now is very important. Questions? Are you okay with this? And they call this joint probability, but we will come, I'll come back to it. Let's look at the questions on 154. And it says, the first one, well, actually, I'm looking at the self-review. Routine physical examinations are conducted annually as part of a health service program. It was discovered that 8% of the employees needed corrective shoes. So probability of corrective shoes is equal to 8%. The probability of dental work is 3%, 15%. And the probability of them having both is equal to 3%. So let's draw the picture so I'm sure that you know what this looks like. 3%. Thank you. So I'm starting in the center. And again, if you don't want to work in decimals, make it 3. Make it 15 and 8 out of 100. So that's what I'm going to do. I'm going to put 3 in here. So how many left needed corrective shoes? 5. I need 8 altogether for corrective shoes. And how many for dental? 12, exactly. And now notice, if I were to mark the rest of this, the universe for me are all the employees at this particular company. And I'm only putting in my circles those that need shoes, those that need dental work. So I'll do it both ways. If I want to know the probability of getting somebody that either has corrective shoes or dental work, from my Venn diagram, I'm just going to add them up. So that's 5 plus 3 plus 12 over 100 is going to give me 20. Or in a decimal, because I'm going to do it in a decimal in a second, it'll be 0.2. if I do it by using the formula, I'm going to get 0.08 plus 0.15 minus those people that required both work. So I'd end up getting 0.2 anyhow. Is that okay? All right, let me go at this in a different way as well. We talked about contingency tables for the last chapter and said we didn't do them, but I'm going to do them now. Only because it makes all of the rules of probability so much easier. All right, I have three factories. Factory 1, factory 2, and factory 3. And these factories are making shoes, hats, and coats. So in a contingency table, what it says that instead of you having to read all sorts of words, we've ended up putting it into a table so you can read everything from the table. And we total both columns and rows, so it looks like this. So let me make up some values here. So how many things were made in factory 1? 180. And here, and how many here? I'll do it. And the last one, and how many in factory 3? 190. How many shoes were made? Altogether, how many shoes? 210. And how many hats? 330. And the number of coats? And altogether, how many items were made? 600. Do you agree? Whether I total it by the total done at each factory or I total it by the number of items made, I must get 600. Yes? If I don't, then I'm not collectively exhausted if I've lost some garment somewhere. So we have different types of probability, and the first type we call marginal. And I remember these by being around the edge. And it would be this. What's the probability if I put my hand into this pile of 600 things that I would get a hat? What would be the probability of me pulling a hat? You got it, 330 over 600. The probability of me pulling a shoe, or a pair of shoes, as the case may be. So that would be 210 over 600. And the probability of me getting a coat? 60 over 600. The probability of me choosing something made in factory 1? 180 over 600. The possibility of choosing something from factory 2, 230 over 600. And the probability of choosing something made in factory 3, 190 over 600. Any problem with that? It's called marginal. It's just straight, you know, what's the possibility of me choosing a man out of this classroom? 2 and 9, or 3 and 11. So we also have what we call joint probabilities when we're adding things together. So in this particular case, what would be the probability of me finding, pulling a hat made in factory 1? Why is this not mine? Factory 1. What's the chances of me pulling a hat and that's made in factory 1? 100 out of 600. What would be the probability of me getting a coat and factory 3? 10 over 600. So this is joint. It means the and. It means that they must carry 2 characteristics. So not only are they a hat, but they must be made somewhere. Oh, and I need to turn the page, but I won't remember these numbers. Can you help me?
Well, someone can write it down. There's no way to do that.
The hats in factory 1 is this number here. Y over 180. Ah, I would then say to you, given that the hat was made in given that it was made in factory 1, what's the chances of getting a hat? So I've already told you it had to be in factory 1. All I'm saying here is when I randomly choose out of my 600 things, what's the chance that it carries both labels? Those are very different. And to do what you wanted, we'll get to it soon, but I would have written this. What's the probability of getting a hat given that? That's that symbol that it was from factory 1. So you're right. I would look at the hats only in factory 1. Okay? So the and just means out of the 600, when I randomly choose one, what's the chance that it will carry both labels? What's the chance that I would find, I'm going to try to write all around this page, okay, because I won't remember the numbers when I turn the page. What's the probability of me getting something from factory 1 and factory 2? Are you sure?
180 plus.
Are you sure?
I don't know.
And means it must wear both labels. It must wear both labels. And that would be me having Prada and Gucci in the same shirt. I think not. 0. When we do a contingency table, nothing in factory 1 has a label, or none of these are going to have 2 labels on them, right? So they either come from factory 1 or factory 2 or factory 3. So the fact that I could draw something that has both labels on it will be 0. What you want to do is to say or. So let me fix it. This is going to be 0. There's no chance of me getting something that will have label of both. But if I wanted to say what's the chances of factory 1 or factory 2, then I would have added them together and got 310 out of 600. Okay, so you're going to have to help me here, or I'm going to have to write somewhere else. Okay, so what would be the chances here? Let's do some more of the joint ones. Okay, over here. What's the probability of getting a coat and factory 1? Yeah. Yes. So I could do every combination here. So when we talk about joint here, we're just looking at where both of them happen. So if I then said to you, I'm going to write at the bottom here, what's the probability of getting a coat or factory 1?
Zero.
No, I can get both. All the coats, all the things from factory 1. What do I have to worry about though? So let's write it. First of all, the probability of a coat, I already know, is 60 out of 600. The probability of factory 1, I already know. It's 180 over 600. But what do I have to take off here?
30.
Yes, the coats that were made at factory 1 have been counted in the coats, and they've been counted in factory 1. So I must take off those 30. And you see how that fits nicely into the formula? Because I did the probability of the coats, the probability of F1, and then I took off the joint ones. So in here, I'm going to end, this should have been 30, shouldn't it? What is happening? 30. All right, well, that's not allowing me to write there. So I'm going to end up with, 270 out of 600. Okay, I should have written this somewhere. Well, somebody can help me. So what would be the probability, the probability of getting a coat or a hat?
So it will be all what?
It's or.
330 over 600.
Uh-huh.
Plus 60 over 600.
And these are mutually exclusive, so I'm not subtracting anything, right? I can't have a coat hat. So here I have 390 over 600, mutually exclusive. If I were to say, what's the probability of getting a coat and hat? No sets sold here, so the answer is 0. The probability of getting a pair of shoes or factory 3. So I'm going to write all the possibility of getting shoes plus all the possibilities of being in factory 3, and from it I must take away all the shoes that were made in factory 3. Do you understand what I'm saying, why we're subtracting? Because we can't count them twice. So how many shoes were there?
Factor 3. 100
100 shoes?
over 600.
Yes.
And
Factory 3?
factor 3, 190 over 600. Subtract
100? Can't be 100. How many shoes were made in factory 3?
100.
Well, then the shoes must be wrong.
210. No, subtract 100.
Okay, that's better. Is that right? That's not right. That's 3, isn't it? 300? Oh, time to go. Questions, we'll redo this again, but do you see the contingency table makes it so much easier to see than in words? So we have a class tomorrow. We'll do it again, and then Thursday will be a review.